Here's a spring. One end is fixed, while the other end is moving. What is the kinetic energy of this spring due to its mass? The definition of kinetic energy, E sub k, is equal to half times the mass times the speed of the mass squared. When the spring moves, every point on the spring moves with a different speed. Therefore, we don't have a simple value that we can use for this formula. To find the kinetic energy of the spring, we need to find the kinetic energy of a point on the spring and then add up the kinetic energy of all the points on the spring. The kinetic energy of a point on the spring, let's call it dEk, equals half times the mass of the point times the speed of the point squared. Now, what's the mass and speed of a point? We assume that a spring's mass, m, is uniformly distributed over its length, L. Therefore, the mass per unit length is m over L. For a point that has a width dl, the mass of the point equals to m over L times dl. Now let's try to find the speed of a point. When a spring moves, every point on the spring moves with a different speed. Let's say in a very short time dt, the end of the spring moves a distance dx. We assume the spring stretches and compresses uniformly. The increase in distance dx is spread out across the entire length of the spring. This increase per unit length of the spring is dx over L. Let's say a point's distance from the fixed end is L. Let's draw a few points on the spring to get a better idea of what's going on. Here's a point at the fixed end. And here's a point 1 unit length away from the fixed end. Here's a point 2 unit lengths away from the fixed end. And here's a point 3 unit lengths away from the fixed end. After the end of the spring moves the distance dx, point 0, it doesn't move. However, the distance between point 0 and point 1 has increased dx over L. So the new location of point 1 is a little further to the right. The distance between point 1 and point 2 has also increased dx over L. So point 2's location is now over here. And the distance between point 2 and 3 has also increased dx over L. And its new location is over here. You can see that the further a point is away from the fixed end, the further it moves. Point 1 moved a distance dx over L. Point 2 moved a distance 2 times dx over L. And point 3 moved a distance 3 times dx over L. So the distance traveled by a point is dx over L times L. And since these distances were covered in a short time dt, the speed of a point, Vp, equals to the distance of the point from the fixed end, L, over the length of the spring, L, times dx over dt. If the point at the end of the spring is moving with speed v, the speed of each point is L over capital L v. So now we have equations for the mass of a point and the speed of a point. Let's calculate the kinetic energy of a point, dE sub k, and that's equal to half times the mass of the point, that's m over L dl, times the speed of the point, and that's L over capital L v squared. And this is equal to half m over L dl L over capital L squared v squared. d E sub k equals to half mv squared over L cubed L squared dl. So that's the kinetic energy of a point. The kinetic energy of the spring is the sum of the kinetic energy of all the points on the spring. To calculate this value, we take the integral of dE sub k. So the kinetic energy of the spring, E sub k, equals the integral of dE sub k. And that's over L equals 0 and L equals L, the length of the spring. E sub k equals dEk is half mv squared over L to the power of 3 L squared dl. And we take the integral from 0 to L. E sub k equals half mv squared over L to the power of 3, and this is L3 over 3. And we evaluate from 0 to L. So this is E sub k equals half mv squared over L to the power of 3 L to the power of 3 over 3, and this is 0. So the capital L's cancel out, and we're left with half m over 3 v squared, and this is equal to 1 over 6 mv squared. For a system with a spring with negligible mass that's connected to a block with mass m sub b and moving with speed v, the kinetic energy is equal to half the mass of the block times v squared. We see that if m sub b equals m over 3, then the kinetic energy of this system will be the same as the kinetic energy of a spring with mass m. We say that the effective mass of a spring is equal to its mass divided by 3.